Space exploration pushes the boundaries of human ingenuity and technology. Powering the instruments and systems aboard spacecraft is a fundamental challenge for many missions, especially those venturing far from the sun or operating in harsh environments. Traditional power sources are insufficient. This is where nuclear batteries, also known as radioisotope power systems, become indispensable. They represent a unique and powerful solution to the energy needs of ambitious space endeavors. These systems harness a natural process to generate electricity. Radioisotope power systems function by utilizing the heat produced from the natural radioactive decay of certain isotopes. As these isotopes break down, they release energy primarily in the form of heat. This heat is then converted into electrical power. The conversion process typically involves thermoelectric converters. These devices generate an electric current when there is a temperature difference across them. The heat from the decaying radioisotope creates this difference, providing a steady flow of electricity. One of the most significant advantages of RPS is their inherent reliability. Unlike mechanical systems, they have no moving parts to wear out. The decay process is predictable and continuous, ensuring a consistent power output over very long periods. This leads directly to another key characteristic: longevity. RPS can provide power for decades, far exceeding the lifespan of chemical batteries or the operational limits of solar panels in certain environments. This endurance is critical for long-duration missions. Furthermore, RPS operate entirely independently of sunlight. This is a crucial benefit for missions exploring the outer solar system, where sunlight is weak, or for operations in shadowed regions, such as polar craters on the moon or during planetary nights. Their ability to function regardless of solar illumination or orientation makes them ideal for missions requiring continuous power in challenging conditions. They provide a constant energy baseline that is unaffected by environmental factors like dust storms or orbital mechanics. The moon presents unique challenges for power generation. While solar power is viable during the lunar day, the lunar night is a significant hurdle. Temperatures plummet, and there is no sunlight for power or warmth. For missions aiming for long-term presence or operations spanning multiple lunar nights, RPS are not just beneficial, they are crucial. They provide the continuous power needed to keep systems warm, maintain communication, and operate instruments through the 2-week-long night. Enabling survival through the lunar night is key to establishing sustained operations on the lunar surface. Without a reliable power source independent of the sun, habitats, rovers, and scientific equipment would need to shut down or rely on limited battery reserves. RPS allow for continuous scientific data collection, resource prospecting, and infrastructure maintenance throughout the lunar cycle. This capability is essential for building a lasting human and robotic presence on the moon. NASA's Artemis program aims to return humans to the moon and establish a sustainable presence. This ambitious goal heavily relies on advanced technologies, including RPS. Power is fundamental to every aspect of the program's long-term vision. RPS technology supports the establishment of a sustained presence on the moon by providing reliable power for habitats, power grids, and operational systems that must function continuously. This enables astronauts and robots to live and work on the lunar surface for extended periods. Furthermore, RPS will facilitate resource utilization on the moon. Power-intensive processes like extracting water ice or processing lunar regolith will require robust and consistent energy sources, which RPS can provide, especially in shadowed resource-rich areas. Scientific discovery on the moon will also be significantly aided by RPS. Instruments and experiments requiring continuous power, particularly those operating in permanently shadowed regions or throughout the lunar night, will depend on these reliable energy systems. Beyond the moon, in the vastness of the outer solar system, sunlight diminishes rapidly. For missions exploring planets like Jupiter, Saturn, Uranus, and Neptune, or venturing into interstellar space, solar power is simply not a viable option. RPS are vital for these deep space missions. They provide the necessary power for spacecraft systems, scientific instruments, and communication over immense distances where solar intensity is too low to be useful. Missions like Voyager, Cassini, and New Horizons all relied on RPS. The compact and efficient nature of RPS can potentially increase the payload capacity for spacecraft. By providing a high power-to-mass ratio compared to large solar arrays needed in low-light environments, they free up mass and volume for scientific instruments or other critical systems. While not a direct propulsion system, the reliable long-term power provided by RPS can indirectly support technologies that potentially reduce travel times for missions. This could include powering advanced communication systems or future high-efficiency electric propulsion concepts. Recognizing the critical role of RPS, several companies and government agencies around the world are actively involved in advancing this technology. Their work spans fundamental research to practical system development. These entities are conducting extensive development of new nuclear battery technology. This includes designing more efficient thermoelectric converters, exploring different radioisotope fuels, and developing safer, more robust system architectures. Simultaneously, significant research is being conducted into the underlying science and engineering of nuclear batteries. This research aims to improve efficiency, increase power output, reduce size and mass, and enhance safety and reliability for future missions. The focus of these development and research efforts is broad, targeting various space applications. This includes power systems for small probes, large landers, rovers, and even potential future human habitats. Several key players are at the forefront of developing next-generation RPS technology. Their contributions are crucial for enabling future space exploration goals. Xeno Power Systems is one such company actively involved in development. They are working on smaller, more modular RPS designs that could power a wider range of missions, including smaller satellites and lunar surface systems. Pulsar Fusion is another entity contributing to the field, though their primary focus is fusion power. However, the underlying principles of energy generation and conversion are relevant, and their work can inform aspects of radioisotope power system design and materials science. The Japan Atomic Energy Agency, or JAEA, is also active in development and research. Their work contributes to the global understanding of radioisotope fuel production, handling, and system integration for space applications. City Labs is known for developing very small-scale nuclear batteries, often referred to as diamond batteries. While lower power than traditional RPS, their work on beta voltaics represents another avenue in nuclear power generation for specialized, low-power space applications. The advancements in RPS technology are being specifically tailored for upcoming space missions. The goal is to provide reliable power solutions for a variety of platforms operating in diverse environments. Technology is being actively developed for lunar rovers. These rovers need to operate through the lunar night and in shadowed regions, making RPS an ideal power source for mobility, instrument operation, and sample analysis in these challenging conditions. Similarly, technology is being developed for deep space probes. Future missions to the outer planets, their moons, or beyond the heliosphere will require compact, long-lasting power systems that can function reliably for decades in extreme cold and low light. These applications highlight the versatility and necessity of RPS. From powering mobile laboratories on the moon to enabling scientific discovery billions of miles away, nuclear batteries are foundational to expanding our reach in the cosmos. The ongoing advancements in nuclear battery technology promise to revolutionize space exploration in profound ways. More efficient, lighter, and more powerful RPS will open up new possibilities. These advancements are enabling new technologies that were previously impractical due to power limitations. This includes advanced scientific instruments, powerful communication systems, and potentially even propulsion systems that benefit from a long-term high-density power source. Ultimately, the widespread availability and improvement of RPS technology will expand the scope of human presence in the cosmos. They are essential for establishing sustainable bases on the Moon and Mars, enabling human missions to the outer solar system, and powering the robotic explorers that pave the way. Nuclear batteries are not just power sources, they are enablers of humanity's future among the stars. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.